Hi and good day to all of you. So we have our new topic for today and for the next few lessons. Okay, under the fault, under the power system analysis, we will discuss fault calculations. So this is under lesson 5. Okay, so first we will discuss symmetrical faults, and then after the formulas and procedures that will be followed by unsymmetrical faults. So we can have a separate video on the derivation of some of the formulas, which is here on your right side of the screen. So by the way, before we discuss this one, so subscribe on my channel so that you can get the additional informations, lectures, and supplementary videos for the lessons that we will discuss. And thank you for all of the support, for liking and sharing and subscribing on my videos. Okay, let us move forward. So you have two types of faults. You have the symmetrical and unsymmetrical faults. So we'll first tackle symmetrical faults. In other words, symmetrical faults are your ISC three-phase faults. Another definition of symmetrical fault is a three-phase fault. So it is defined here as the faults in a power system where the conductors are simultaneously short-circuited. So you already know what is a short circuit all about. If you have two conductors that are live, don't do it at home. Your conductors are live and then you put it together, connect it together, it will produce short circuit. Now in this case, since we are on a power system, definitely we are in a three-phase, three-wire system. You have a three-phase, three-wire here. By the way, fourth wire, rather, three-phase, four-wire, to include the ground or neutral here. Okay, so there is a fourth wire, which is not seen on the drawing. That to have a short circuit three-phase, you have your loads that are balanced from our past lesson. To have a balanced load, you have equal impedances. Your lines or voltages on the terminals, okay, these are your terminal points. The voltages there at the source is balanced as well, so you're considering a balanced system. So please take note, the analysis also of symmetrical faults is also balanced polyphase. So if you have a short circuit here, that the three wires on your load are simultaneously short circuited, it will develop balanced fault currents, which could say IFA, IFB, and IFC. And this balanced fault currents is also called your symmetrical fault currents, which is, in other words, this is your ISC three-phase. And by using per phase analysis, you can get IFA, IFB, and IFC in terms of magnitude. But again, since that is a balanced polyphase, the difference between IFA, IFB, and IFC are 120 degrees apart. With respect, again, to our phase A as our common reference. Okay, thus, how can you compute short circuit current? Short circuit current can be computed by the reactances of your elements. From your per unit analysis from the previous lesson, these are your reactances on your generators, transformer, your lines, etc., which can be computed and can be converted to per unit. So we will not go to the per unit. You can go back to the last lesson, and from here we can compute short circuit currents. And please take note that you can compute symmetrical fault by using again your basics on Thevenin's theorem, which is one of the application of Thevenin's theorem is this short circuit analysis. So from here, you need to get the Thevenin's reactance up to the fault point. Okay, we can have that when we go forward to some of the problem solving. But again, since this is a very, very big lesson or a subject by the way. So the definition, the explanation further of having Thevenin's and Norton's equivalent applications and even superposition will be discussed on a separate video. Okay, since this is just a crash course or a refresher course. And hence, we need the formulas, which is simply equal to get the short circuit current, you need to get the I base. And very basic. I base is equal to S base all over square root of 3 of the base voltage. We already described this one during per unit analysis. That's why our first topic is per unit or modeling. And then KVA short circuit is KVA base times IPU. And then the per unit current is, again, since this is a Norton's current, short circuit current, which is converted to per unit, is whatever the Thevenin's voltage all over the Thevenin's impedance up to the fault point. By the way, Norton current, no, is TEC and EC can be converted to each other by using your Ohm's law, right? So you can go back to your Norton's, and Norton's current is also the so-called short circuit current. So that's why we name it as IPU, because it is in terms of per unit. And please take note that VTH per unit is the pre-fault voltage. By the way, this is assumed, no, for our discussion, that your pre-fault voltage per unit always equal to 1 in this case. But to get the VTH actual, you need to get the operating voltage, actual voltage all over whatever the base voltage is on the system. Okay, so this is in terms of per unit value. So let us go to the next slide for the procedures on how you will get fault currents, especially three-phase currents, three-phase fault currents. See you. Hello once again. So here we will discuss the other formulas that we can use for the fault calculations, and these formulas are important for the problem solving on our next topic. So let us have first how you convert per unit reactances given a percentage reactance on a certain transformer or generator. We use the forever formula as we have recalled on our per unit analysis. So this is the forever formula, wherein S base is our forever here, and then you divide it by S given, V given over V base, you squared it, and then multiplied by whatever the reactance is. Please take note, it can be reactance, impedance, or resistance for flexibility. Okay, we use here, as you can see, if V given is equal to V base, if you have a system wherein the given voltage is also equal to the base voltage, or simply, in other words, if you have the pre-fault voltage, that is always equal to 1. Simply because V given is equal to also to V base. If you divide it and you want to get the per unit voltage, the answer is 1. So if that is the case, then we can have a more simplified form of the forever formula, wherein it can be X new is equal to X old multiplied by S base all over S given. Please take note, given is old and also rated value. Okay, now how we will convert now passive elements to per unit. Okay, so this is our values of your impedances or your reactances or your resistance, wherein you want to convert ohmic value to corresponding percent or per unit. So how you will do that? We can have this mnemonic, which I can share with you. Okay, the spheres of destiny. So sorry if you are a fan of Final Fantasy or Star Ocean, so those RPG games on your PlayStation, you usually have the destiny word. So this is just a mnemonic wherein you can use your SODs. No, it can be 1, 2, or 3. Then the answer is still the same. Choose your path, choose your path, choose your destiny. choose your fate. They're the same. So here, we can have the first sphere of destiny, converting ohmic value to its corresponding percent. Now, the X here definitely is an ohms per phase. So, considering a three-phase system, it must be ohms per phase. The voltage here is in a per phase basis, so it must be line to neutral voltage. So, please take note of those important parameters. IFL here, simply, this is your base voltage. And the base voltage here is S base all over square root of 3 times V base. This is from your per unit analysis, right? So all of the full load currents there is your I base. Okay, this is your SLD number 1. Percentage X is IFL times X all over V times 100%. Now, if the given is impedance, all you have to do is have in Z, or if the given is resistance, have it this one in R. So it is flexible. I just use X here for reference. Okay, you already also have sphere of destiny number 2. So this is my favorite and common, but I did not derive this one. I already showcased this one as a pre-derived formula. Percentage X is kVAX all over 10 kV squared. Please take note that the kV here is your S base and S total. Your kV here is the fault point voltage, which is, I could say, V base or V fault. And please take note, it must be in a line-to-line basis. So another formula, sphere of destiny number 2. And last but not the least is the sphere of destiny number 3 that we usually use on converting passive elements or in your transmission line and loads to its corresponding per unit. As usual, this is based from per unit is actual all over the corresponding base. So in this case, you have X actual over X base. However, since we're considering ideal transformers, Z base is also equal to X base equal to R base. Now recall, to get Z base KB squared over MVA and rearranging the equation, substituting this Z base here, we can have this value in percent. So instead of per unit, just multiply it by 100 to become percent. So percentage X, MVAX, all over kV squared times 100%. So please take note, that we can have a flexibility here. So you can have Z here, you can have R. So it depends on the given. Okay, so these formulas are very, very useful. So you can use this on the calculation part on our next topic. So again, please stay tuned. Now, let us discuss the procedure for fault calculations, especially on your ISC 3-phase. So if you have a loaded power system, it means that you have already a big power system. This is the procedure that you must use so that you can arrive at the short circuit parameters or the formulas that we have discussed a while ago. And please take note, it is this procedure is, I coined this term as a 6-point algorithm. 6-point algorithm or 6-pa. So it means point algorithm. You have a series of procedures here that, of course, that computes for the important parameters of the system, which is this short circuit parameter. So I coin it a 6-point algorithm. So you need to have the 6 procedures here so that we can compute for the fault current. Okay, let us have the first procedure. So you need to have the single line diagram in terms of per phase of the system. So we use phase A as our reference. And please take note, it must indicate the percentage reactance or per unit reactance. By the way, if the given is R and X, you have percentage impedance, or the given is only resistance, that is percentage resistance. So it can be flexible, it can be an X, R, or Z. So it must have those parameters, the ratings, the powers, and the reactances. Okay, number 2, choose a numerical value of your S base. So you can have any number that you want, which is the same way on per unit analysis for these problems. And then convert all of the old reactances from 1 to its new reactance using, well, our coined forever formula. Okay, using the forever formula, we will make use of that as well here, which is very clear that you need to draw the per unit equivalent diagram first before you analyze it, right? So our first topic is more on single line diagrams from lesson 4.3, if I'm not mistaken. So from there, okay, we need to draw the per unit equivalent diagram first. And then it is called a reactance diagram on your per unit analysis. Okay, the only difference is it is like a per unit equivalent circuit, but the sources are now shorted or zero. Why? Because it is very important, because on your Thevenin's equivalent, to get XTH at the fault point F, you need two zero sources, right? So if that is a current source, you need to open, and you have your voltage source, you need to short. Considering there are independent sources, or it means that your sources are, okay, in a circle type. Because it is different if that is a independent sources like this, which needs a, or dependent sources like this, which is dependent on current or voltage. But in this case, our sources are independent, so we are lucky to have shorted or open. So we will short all of the sources to zero. And it's like a per unit equivalent circuit with the voltages are shorted. So draw the reactance diagram. This is what I meant with your reactance diagram. It's like a per unit equivalent circuit where the sources are zero. And then connect these sources and model it as a reactor and connect it to your common neutral. Okay, number 4. Determine the Thevenin's equivalent up to the fault point F using your basics of your circuits. It can be a series, parallel, or even on complex systems, especially in subtransmission, delta to Y conversions. Okay? Then number 5, we need to compute for the base current, which is very important in computation of short circuit current, and the per unit current. So from what we have described from the last slide, we will make use of your BTH or your pre-fault voltage as 1. So IPU is 1 all over XTH at F. So get XTH, then inverse of that, you will have IPU. And then from there, we can compute for the short circuit parameters from the formulas that we have from the last slide. ISC 3-phase is I base times IPU, and KBA short circuit is KBA times IPU. By the way, another term for a KBA short circuit is rupturing capacity of the breaker, or the so-called symmetrical short circuit KBA. Sometimes it is called a dead short circuit KBA. So if you experience these terms, no, some of the problems, it is your KBA short circuit, the total energy that can disbombard or can destroy your circuit breaker. So you need to have these limits on your protective devices. Okay, so we can move forward to our next topic or set of formulas for unsymmetrical faults.